All right, ladies and gentlemen, class recording for today has begun. So, up on the board, right, as I had you guys working on the last 2 minutes, those are your objectives from yesterday. So, let's review quickly. First, radioactivity, why it occurs. Sum it up for me in like one sentence. Who wants it? There's good. Why? So, sorry, wait, sorry for the recording. Radioactivity is when the nucleus is unstable. Why is the nucleus unstable? Strong nuclear force isn't strong enough to hold it together because what's in the nucleus of an atom?
Protons.
And what do those protons do? Repel each other, right? So it has to do with the fact that there is too much repulsion in the nucleus for the strong nuclear force to hold it together, right? All right, compare and contrast 4 types of natural radioactivity. So the one comparison we could say of all 4 of them is what are they trying to accomplish? When one or all of them occurs, what happens in the nucleus? Lower energy state. It becomes more stable, right? 3 of the ones we talked about has something in common. Alpha particles, beta particles, and neutron emission have something in common. What are the things that they all have in common?
They emit particles.
They emit particles, or they emit, all those particles would be considered matter, right? Particles, matter, same thing, right? Then the difference being gamma radiation, right? Gamma radiation is what?
Electromagnetic radiation.
Electromagnetic radiation, it's carrying what?
Energy.
Energy, right? So those are the big contrasting ideas there, right? Was it, no, it's the other class, never mind. All right, one thing that we talked about yesterday is that there is some combination of different things that can happen. And if you look at what the different types of radiation are, alpha particles, beta particles, neutron emission, you might be a little confused. Well, wait a second. If I, first, we talked about a beta particle. What is a beta particle? An electron. But, Suzanne, where does it come from? Well, yeah, right, but it comes from what part of the atom? Radioactivity deals with the nucleus, right? So that would, be like, wait a minute, why are electrons coming out of the nucleus, right? But we kind of talked about the idea that a neutron has the ability to sort of fall apart into a proton and electron, but then you might say, well, wait a second. If the electron leaves the nucleus and the proton is left in the nucleus, doesn't that make it even more radioactive, right? We said the biggest problem is that there's too many protons. Well, yeah, but sometimes what we find out is that it's not, like I mentioned this to you yesterday, I think a couple times, it's not straight up the number of protons that's the problem. A lot of times it's the ratio of protons to neutrons. And in some ways, they might gain a proton in order to emit more of them later on, like more alpha particles or whatever it is. So it's not just a straight up like one step and it's neutral. A lot of times atoms have to go through several steps in order to become fully stable. Okay? And then the last one, half-life. When we're talking about half-life, what do we talk about? You good?
The time it takes for half a radioactive sample to decay.
Half a radioactive sample to decay, right? And so that then continues on, right? So every time a half-life goes by, we lose half of the sample. And when we say lose, basically it's becoming more stable, right? When we say it's radioactive and now it's not radioactive, that means it got more stable. So it doesn't emit energy, it doesn't emit radiation, all those things. Okay? Good there. Eric's good.
How strong is the neutron emission?
What do you mean how strong is it?
Like compared to like the alpha particle and the beta particle, like
So going back to like this particle, or this picture, right? Okay. Actually, neutron emission is actually really, it penetrates quite a bit because what do we know about a neutron? And this actually will transition well into today's discussion too. Why would, here, let's do this. If we add neutron emission to this picture, here, let me grab this, and stand by, everybody. Stand by. Okay, so let me grab this picture here, all right, and I'm going to trying to do this on my there is the picture that shows the different amounts of penetrating power of the different types of radiation. If we add neutron emission to this, it's very similar to gamma rays, and in some cases even more so than gamma rays. Okay? I would like you to have a 30-second discussion with the person next to you. Why might a neutron be able to penetrate through these different types of matter farther than, say, an alpha particle or a beta particle? Discuss. Go. Okay. So, earlier we said that there is something similar about these three, right? What's similar about those three? They're all matter, okay? But there's something different about neutron emission than it is about alpha particles and beta particles. And what's that difference?
The charge.
The charge, right? And the fact that it has
A neutral charge.
a neutral charge. It doesn't have a charge, right? So as it passes through these different matter, right, we said that most of the atom that make up this, this, and this, most of the atom is what? If we looked at an atom, most of its volume is what? Empty space, nothing, right? So as that neutron is passing through, right, it really doesn't get affected if it comes close to a nucleus or if it comes close to an electron. It just doesn't do anything. Unless it's a direct hit, those neutrons will pretty much go straight through and not be affected by anything. And we talked about earlier with the odds of a direct hit are actually pretty small, right? Because most of that nucleus, or most of that atom is empty space. So, Eris, so neutron emission, to answer your question, neutrons actually go through quite a bit because of the fact that they aren't affected by those other nuclei that they might come close to, or electrons or things like that. Okay?
So since alpha and beta are charged, they are attracted to what's inside the atom?
Exactly, right? And alpha particles, we said alpha particles are 2 protons and 2 neutrons, right? So they're actually really big. So going back to this picture, Andy, right? Alpha particles run into a lot of stuff because they are so big and because they are affected by other nuclei. You're either repelled or things like that, but they're really big, so they run into stuff. Electrons are affected by nuclei, right? They're attracted to nucleus if it comes close, but because they're so small, they have the ability to penetrate a little bit further, right? Gamma radiation goes straight through because it's not matter at all. It's like energy, right? But then neutron emission, because it's, you know, it's bigger than an electron but smaller than an alpha particle, right? So it has that ability to basically kind of go through and not be affected unless it directly hits a nucleus. Okay. All right, good there? That's actually a good transition into what we're going to do today. So, at the end of class yesterday, we began our discussion of nuclear fission. So, nuclear fission first gets proposed, explained, published in a paper by 2 scientists, Lisa Meitner and Otto Frisch in 1939. And I think that we kind of discussed the backdrop a little bit of what was going on at that time, right? You know, 1939, the Nazis are in power in Germany, right? That's when they start moving eastward. I think 1939 is when they move into Poland, if I'm not mistaken, right? So really, we're at the very beginning of World War II, starting up. You know, things are starting to happen, and you know, socially, right? Meitner is a Jew, so she gets herself out of Europe altogether. First, she leaves. I think she's Austrian, if I remember correctly. But she leaves Austria and goes to Scandinavian country. I think it's Sweden, if I remember correctly. And then eventually makes her way to the United States. But the other guys she's working with, Otto Frisch and Otto Hahn. Otto Frisch, if I remember right, is her nephew, and Otto Hahn is kind of like her teacher, like in when she was getting her PhD, you know, one of her instructors, stuff like that. So anyway, but they continue a lot of this work through the mail, that they do experiments on their own, and they send the results to each other for comparison and kind of checking it over to see if they get that. But what they realize is this. if we take a large radioactive nucleus, it's going to decay on its own. That's what it's going to do. It's going to lose alpha particles, beta particles, neutron emission, not all three of them necessarily, but in some fashion, it's going to decay and become more stable. What if we just kind of gave it a little push, and instead of little bits coming out of the nucleus, you know, an alpha particle here, a beta particle there, and in a slow, sort of drawn out process, it becomes stable. What if we could make it happen all at once? Right? For example, if we look at uranium, okay? Uranium has an atomic number of 92. We talked about earlier in this outline that in order to become stable, the magic number for protons can't be bigger than what? 82, right? So to become stable, uranium has to lose how many protons? 10. Can't lose all 10 at once, right? An alpha particle only has 2. So in some process of alpha particle, beta particle, neutron emission, it has to lose 10 neutrons. That takes time, and over time it continues to lose particles, continues to lose energy, and becomes stable. Scientists start realizing that maybe we could just kind of make it all happen, boom, all at once. One step, it splits, it becomes stable, and all of that energy that it released over time, we could release it in one moment. Right? So, the realization comes out of that is that tremendous amounts of energy are released from a very small amount of radioactive material. And we'll talk about why here in just a second. So, if we could make this happen, as this atom is decaying, it continuously loses energy. That's the process of getting more stable, right? Losing energy. So if we could do it in one step instead of many small steps over time, all of that energy that it would have released over thousands of years, maybe even millions of years in some cases, if we could release all that energy at once, we could harness it and use it. And so we get this picture. Okay? Now, there is space around that picture for you to make some notes. I'm going to throw some things up here on the board to highlight some of the things. Right? So first, we start off with uranium-235. Scientists have tried to recreate fission with lots of different isotopes, but they have only been successful in creating this fission reaction with 2 isotopes. One is uranium-235, and one is plutonium-239. Okay? They've tried it with all kinds of other things, but what they find out is that when they do what they're supposed to make fission happen, and we'll talk about the details here in a second, it doesn't like split in half. It just doesn't. Right? It kind of absorbs the neutron that we're going to shoot at it, and then it just sort of little bit by little bit goes through its radioactive decay. So uranium-235, plutonium-239, those are the only 2 isotopes that actually do this. So you can't just take any radioactive isotope and make it happen. It just doesn't happen. They've tried, but it just doesn't happen. Okay? So here's the gist. First, you get a neutron, and you shoot that neutron at this uranium-235 nucleus. Okay? As I discussed from our as I kind of mentioned in our discussion a little earlier, why does a neutron work better than something else?
It's smaller.
It's smaller, right? But another thing too, it doesn't have a what?
Charge.
It doesn't have a charge, right? So it's going to go in a straight line and not be affected by other stuff. Okay? Would a proton work better? Sure, a proton would work better. But there's no type of radioactive decay that gives off a single proton. Okay? This neutron comes from some other radioactive substance that's giving off neutrons in neutron decay. If we can harness that and use those neutrons to shoot at this uranium-235, right, then we have a neutron running into this nucleus. Neutrons have no charge. Their motion will not change as they move closer to the nucleus, right? You might say, well, wait a second. There are some radioactive materials that give off electrons, right? Wouldn't an electron work? Because an electron would be attracted to this nucleus. We'd be sure to hit it, right? But what do you know about electrons versus neutrons?
They're a lot smaller.
They're a lot smaller. We run an electron into a nucleus, nothing happens. Okay? And a proton is the same size, right? But you can't use a proton, why not? It never gets there, right? It gets repelled by the nucleus and doesn't run into it. So a neutron works best. Okay? Now, when the neutron runs into this nucleus, right, a couple things happen. First, it's not just as clean as I'm going to give it to you right now, but here's what happens. It basically is kind of like hitting it with a, like, not a hammer. I totally forgot the word I was going to use. A chisel. That's what I was going to say. It's like hitting with a chisel. You split that nucleus basically in half. Not exactly, but into two smaller nuclei that are below the 82 proton limit of being radioactive. Okay? Now, if you've ever seen somebody use a chisel before, either on wood or maybe you've seen somebody like do an ice sculpture, right? When they use a chisel to break something in half, first of all, I'll be okay with a chisel, right? It's like a kind of a spiky thing, and you hit it with a hammer, and it cuts the thing in half, right? When you use a chisel to cut something in half, is it real clean that it just breaks into two parts? You ever see somebody do an ice sculpture? They, what happens while they're using that little chisel? They might break it in half, right? But
Some stuff goes flying
little chunks kind of fly off. And that's what happens here, too. You get these two big nuclei, which is great, but you also get a couple of stray neutrons and lots and lots and lots of energy. Those purple waves that they're showing up in this picture here, we would categorize them as what? That's gamma radiation, right? Now, these neutrons that come off aren't necessarily neutron emission. They're just sort of leftovers from this process. So you take this neutron, it acts kind of like a chisel. It comes into this big radioactive nucleus that would decay on its own anyway, and just sort of expedites the process, makes it go a little faster. Instead of being, now, going back, in no way naturally would this big uranium-235 split into these two. It goes in little chunks and ends up as something a lot larger that's more that's stable, right? It doesn't do this naturally. Fission is not a natural process, okay? But we found that under the right conditions, certain isotopes do this. Like I said, not all isotopes. You can't take any radioactive atom and do it, okay? Only certain isotopes. Uranium-235, plutonium-239. So the only two things that we know of that will go through this process, okay?
How did you say the neutron splits the uranium?
Yeah, it's Andy, that's kind of like the chisel. The neutron is like the chisel. It comes in, and as it hits that nucleus, it splits it into two pieces.
Oh,
Okay?
okay. I thought you just meant like somehow it just like split it without like actually getting shot at it.
No, you have to have this neutron to basically get it started. You know, like I said, this process, like, Andy, we couldn't do this. Here, what am I looking for? There it is. Okay. You can't just sit around and wait for this to happen out there in nature, right? This does not happen naturally. This atom would never split into these two smaller atoms and these two neutrons on its own. But Just like a chunk of ice would never split into two chunks of ice without hitting it with a chisel, right? You can sit there all you want to, it's not going to happen, right? But if you add something into this, right, you add this neutron into it, and now you can make it happen.
Okay.
Is that good? All right. But yeah, it doesn't happen on its own. Now, here's the weird part. And if it's weird, that means probably Einstein is involved, is the case. So here's what we find out. Earlier in the year, we talked about conservation of mass, right? And we use it to balance equations and all kinds of stuff like that. But what we find out is during this nuclear reaction, if you take the mass of these two things together, okay, which would be considered what in this process? What part of the process are those two things? Those are our reactants, right? That's what's there to begin with, right? And then you take the mass of this stuff over here. What you find out? Not the same. Now, we're talking about the nucleus of an atom. So the difference in mass is very, very small. But still, if you take the mass of these things together, and you take the mass of all of this stuff together, not the same. Which seems like a violation of conservation of mass. But we find out that it's really not. Because of this little thing right here, the mass energy equation. I'm betting you've probably heard of it before. Okay? First, proposed by Einstein in 1905, which is way before fission and fusion were even discovered. So this is not something that Einstein came up with to explain why fission works, or to explain why what happens during fission happens. This was proposed way before that. But it applies to this situation. And perhaps you've heard of this equation before. Okay? Yes? Heard of this one before? E equals mc squared. Okay? Now, E equals mc squared is a weird part of a much weirder theory of relativity, which we're not going to get into. Okay? But this is an important part as it relates to fission, because first, this is an equation, and since you started taking pre-algebra back in whenever it was, 6th grade or 7th grade or whatever, you learned that if you have an equation, what has to be true about both sides of the equation? They have to be equal. That's what an equation is. This side equals that side, okay? So if we look at this equation, right, on the left-hand side you have an E. Any guess what that E stands for? Energy. And on the right-hand side, you have an M. Any guess what that M stands for?
Mass.
Mass. What Einstein proposed is that energy and mass are two forms of the same entity. Yeah. Kind of made this face. So, which kind of you're not the only person that makes that face when we talk about this. Okay? That under the right conditions, we can convert mass into energy, and we can convert energy into mass. Okay? Yeah. Mark made this face. Which, yeah. It's a weird concept, but we have lots and lots and lots of experimental data that backs up the claim. Okay? So first, just as this, right? There's the three things that show up in that equation. E is energy, M is mass, and C we introduced in the last chapter being the speed of light. Now here we can actually make that a little bit more general. It's not just the speed of light, we could also say it's the speed of what? Light is just one specific form of any electromagnetic radiation. So it's the speed of X-rays, and it's the speed of gamma rays, and it's the speed of radio waves as well. Okay? We always kind of talk about it in terms of light, but light is really just one specific form of electromagnetic radiation. So, consequences. no, sorry, you guys didn't. I added this after I had that sent to the printer. So this does not show up in your outline, but if you want to jot some things down, it might be good to know, right? First, as we discussed, mass and energy are two forms of the same thing. And under the right conditions, mass can be converted into energy, and energy can be converted into mass. And the big picture, at least in terms of this, right? What that means, if we go back, I'm sorry, did we have that or? Okay, we got those two things. So, big picture, let's go back to this. So we said that if you looked at the mass of the stuff circled in red and the mass of the stuff circled in blue, it doesn't come out the same. Which one should be smaller? Yeah, the blue, right? Because what else do we get out of this process?
Energy.
Energy. The difference in mass from red to blue is made up in the energy that is released. So we've talked about two important conservation laws so far this year, and you will continue to use them when you go to chemistry and into physics. What two conservation laws have we talked about so far this year?
Law of conservation of mass and law of conservation of energy.
Law of conservation of mass and law of conservation of energy. Are they really two separate laws? According to Einstein's equation, you can't have one without the other. So if we really want to talk about an object that conserves mass or conserves energy, we have to talk about them both together. Now, here's the part that makes this process release so much energy. Going back to this equation. Right? There it is. E is energy, M is mass, C is the speed of light. We learned earlier, and I just up there on the board right now, the speed of light is 3.0 times 10 to the 8th, or 300 million. 3 with 8 zeros after it. Okay? Let's say you put 1 gram in for M here, that we want to turn 1 gram of mass into energy, right? 1 is fine, but then what are you multiplying it by? A lot, right? 300 million, but it's not just 300 million, 300 million squared, right? So
90 quadrillion.
yeah, 90 quadrillion, is that 12 zeros?
16.
16 zeros, right? So even if we could turn 1 gram of matter into energy, you would get 9 with 16 zeros after it worth of energy out of it.
Never mind.
Okay. Is it too much? Is it too much to think about, Andy?
It's too much to handle right
It's too
now.
much to handle. All right. So even if, right, the end result of this being, when mass is converted into energy, tremendous amounts of energy are released from just very tiny, small amounts of mass. Now, if you split 1 atom, does that give you tremendous amounts of energy?
No.
No. Because, and I don't expect you to remember this, but if we start talking about the mass of an atom, we're talking about 10 to the negative 27th power, right? We're talking about 10 to the negative 27th power. So even though c squared, Mark, you said was how many zeros? 16 zeros, right, after the number, an atom is 27 zeros before the number, right? So one atom doesn't do a whole lot for us. But, like we said, a very small sample of some radioactive material has how many atoms in it? Lots or little? Lots, right? You know, we talked about Avogadro's number, 10 to the 23rd power, blah, 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 right? Now we're starting to get somewhere, okay? So even a very small amount of matter that can be converted into energy releases a huge amount of energy, okay? Good there. All right, that's a good stopping place for today. Tomorrow we'll talk about how we harness all this energy and use it for evil and destructive ways, but not always, just sometimes.